Lists are everywhere in programming. Sequences, vectors, streams. They are the default container in almost every language.
But arrays are more cache-friendly and hash maps look up faster, so why won't lists just go away?
The honest answer is not convention, and it is not ease of construction. It is algebra. A list is the free monoid. It is the most general monoid you can build from a set of generators. And once you see that, a whole family of operations stops looking like design patterns and starts looking like theorems. In particular, fold. The operation that walks a list element by element and combines them is not something we invented. It is forced. By the end of this episode, fold will be a theorem, and lists, multisets, and polynomials will all turn out to be the same idea wearing different clothes. Start with a set S of generators, maybe just a few symbols. Call them A, B, and C. The free monoid. On S is the set of all finite sequences of elements drawn from S itself. The operation is concatenation, stick two sequences end to end, and the identity is the empty sequence, which changes nothing when you concatenate with it. That is a monoid, an associative operation and an identity. So the type of list over a set is exactly a monoid. The word free is doing real work here.
Free from what exactly?
Free means no equations hold, except the ones the monoid axioms force on us. Associativity holds because it must. Identity holds because it must, but nothing else. We do not impose commutativity, so the list consisting of A and B is not equal to the list consisting of B and A. We do not impose idempotency, so the list consisting of A and A is not equal to the list consisting of A alone. Every distinction that could survive does survive. That is what makes it the most general monoid on S itself. And there is one more fact that turns out to be the key to everything. Every sequence is a product of singletons. The list consisting of A, B, and C is the singleton A, concatenated with the singleton B, concatenated with the singleton C. Each generator enters as a one-element list, and concatenation assembles them. Hold on to that, because it is exactly what lets a single function on generators determine a function on the whole structure. Here is the universal property. The heart of the matter. Suppose you have any monoid M and any function f that sends each generator in S to an element of M itself. Just the generators, nothing about lists yet. The universal property says there is one and only one. Monoid homomorphism, call it f-bar, that extends f from the generators to all of the free monoid on S itself. And the formula for it is forced by what we just saw. Since every list is a product of singletons, f-bar of a list is forced. Apply f to each element in turn. It is f of the first element times f of the second, and so on down the list. All combined with the monoid operation of M itself. You define f on the generators, and the structure does the rest. Look at what that formula actually is. Take the elements one at a time, apply f, and combine into a running result using the operation of M itself.
Wait, isn't that just fold?
That is fold, that is standard accumulate, that is standard reduce. The universal property is telling us that fold is the only structure-preserving way to interpret a list inside a monoid. Any function that respects concatenation and identity has to agree with fold. Two consequences fall right out.
What happens on the empty list then?
First, fold over the empty list returns the identity element of M itself. Not by convention, but because a homomorphism must send the empty sequence, which is the identity of the free monoid, to the identity of M as well. And second, fold of a concatenation equals the combination of the two folds. You never have to verify that. It follows from the construction, because f-bar is a homomorphism by definition. Now let us pin the call and never touch it again. Extend of f applied to a list excess. This is fold, our unique homomorphism.
We really never touch the code itself.
Never, we will hold this call fixed, and only change the target monoid m and the function f itself. Same algorithm, swapped structure. Send m to the integers under addition, with identity 0, and let f be the identity on numbers. Fold the list consisting of 1, 2, and 3. You get 1 plus 2 plus 3, which is 6. That is sum. Standard accumulate with plus is this exact homomorphism. Keep the same kind of list, but send m to the integers under multiplication, with identity 1. Fold the list consisting of 2, 3, and 4. You get 2 times 3 times 4, which is 24. That is product. Nothing about the algorithm changed, only the structure underneath it did. Send m to the integers under maximum, with identity the lowest possible value. Fold the list consisting of 3, 1, 4, 1, and 5, and the running maximum lands on 5. Now send m to strings under concatenation instead, with identity the empty string. Fold the list consisting of hello, space, and world, and you get hello world. Maximum and string building are the same fold, in different monoids. Even length is an instance. Map every element, whatever it is, to the number 1 and fold in the integers under addition. The ones add up to the count. So for a list of 3 strings, the result is 3.
So length is really just counting in disguise.
Length is a monoid homomorphism from lists to the integers. Every one of these, sum, product, maximum, concatenation, length, is the same theorem, evaluated in a different monoid.
The free monoid never lets us commute elements. What if we just add that in?
Then sequences collapse. If we declare that order no longer matters, the list consisting of A and B, and the list consisting of B and A become the same object. What we get is the free commutative monoid. And its elements are multisets, also called bags. Order is forgotten, but multiplicity is kept. The bag consisting of A and B equals the bag consisting of B and A, but the bag consisting of A and A is still not equal to the bag consisting of A alone. Concretely, a multiset just records how many of each element you have. The operation is union, which adds the counts. Take the bag containing the element 1, appearing once, and the element 2, appearing twice. Union it with the bag containing the element 2 and the element 3, each appearing once. The element 2 now appears 3 times, 2 from the first bag plus 1 from the second, while 1 and 3 appear once each. 5 elements in all. It is the same fold idea, now living in a commutative structure. And this is a ladder you can keep climbing. Start with the free monoid, associativity and identity only, and the elements are sequences lists. Add commutativity, and you get the free commutative monoid, whose elements are multisets. Add inverses, and you get the free abelian group, whose elements are signed multisets. Add the full ring axioms, and you get the free commutative ring. Each rung imposes one more equation, and each equation collapses more elements together. The free monoid is the most general, and the most constrained rung on this ladder has a famous name.
Polynomials, that is the famous name, isn't it?
Exactly right. A polynomial in one variable over A ring R is exactly an element of the free commutative algebra. Over R on a single generator, the generator we usually call x itself. The coefficients live in R, and x is just a free generator that we have agreed to let commute and obey the ring axioms. Polynomials were a free algebra all along. And evaluation is the universal homomorphism, one more time. To evaluate a polynomial, that is C0 plus C1 times x plus C2 times x squared and onward. Pick an input and call it A itself. You send the generator x to A itself and let the homomorphism carry everything else. X squared goes to A squared, x cubed to A cubed. And the result is C0 plus C1 times A plus c 2 times a squared, and so on. That is extend. With the generator mapped to a point, plugging in a number is the same construction as folding a list. So these structures are not design choices. Lists appear everywhere because the free monoid is universal. Any computation that respects associativity and identity factors through it. Multisets appear in combinatorics because the free commutative monoid is universal for commutative computations. Polynomials appear in algebra because the free ring is universal for ring computations. The free algebra on a set of axioms is the inevitable starting point. The structure you get before you impose any problem-specific equations. Algorithms arise from algebraic structure. Free algebras tell you which structures are the starting points.